vector fields which are derivatives of mapping functions. They give the basis of these tangential vector fields. Any tangential vector field can be represented as the sum, finite sum of these derivatives with certain coefficients. So that means that these functions, derivatives, are basis in the tangential vector field, tangential vector fields. In the space around surrounding space, ambient space, Euclidean space, we have a natural basis, which is this one. When you have 1 at one place of the vector and zeros at all other places. So it's the natural basis, and this is the natural basis on the surface. Okay. This was about surfaces and the vector fields. Now another definition. Another definition is simpler. You have some function which is smooth function, has derivative, and you consider all points where this function is equal to 0. If the gradient of this function is not 0, that means that the derivative of this function never is 0. Never is 0. I mean, it has n derivatives. One of these derivatives, I mean the gradient of this function, will not be 0. At least one of the derivatives is not 0. If we have such function, then zeros of such function gives you this surface again. Gives you this surface. For example, the sphere, unit sphere can be defined by this. No, I think one can see this without. Yeah. For this sphere, unit sphere, when you have the radius 1, radius is equal 1. For this, you have very simple x1 square plus x2 square plus xn square is equal to 1. This is the, or to minus 1 is equal to 0. This is exactly this function psi x, which gives you this surface. And any surface can be defined this way. Any surface can be defined this way. You take certain function, it always exists. This first and second definition are equivalent. You take certain function, they exist function which gives you your surface. And the gradient, we will use this gradient, this notation for gradient of psi. Here is written S also, this surface. Gradient of this function, which means a derivative, first derivative by first variable, so on, derivative by n variable, is not 0. That means one of these derivatives at least is not 0. This is the, we require this, that this will be the surface, otherwise it cannot be surface. And it's interesting that this gradient, if we divide it by its norm, gradient, and then divide it by the norm, this is the vector, it has norm in Euclidean space. Gradient of psi, then it is exactly this normal vector field. So at this point, you have vectors orthogonal to your surface. It is given by this function. So it's very useful to define very simply the normal vector field, which will play a crucial role in our calculus of differential equations on surfaces. You have normal vector fields, which are defined by this implicit function, certain implicit function which gives you the surface. So these are two definitions which are useful for us. Here is written exactly this gram matrix, which gives you the measure on the surface. Okay. Now let us consider here is written what I have written there. The normalized gradient of our implicit function, which gives you surface, gives you the unit normal vector field. And also what is good, this function is defined not only on the surface, but it's defined in the neighborhood of the surface. So you can continue this way. This normal vector field not only on the surface, you can have it in the neighborhood of the surface. So you can continue it in the neighborhood of the surface. You have this normal vector field extended in the neighborhood of the surface. So you have some vector field in the neighborhood. It's important because we will use it. And very interesting property of this normal vector field is this one. Look here. The derivative of this normal vector is vector. Yes, normal. This is vector. It has n components because it is embedded in Euclidean space. Nu 1, x, so on, nu and x. So it's vector. And now you take each component of this and take derivative. This yacht derivative of the k component. And it is equal to k derivative of yacht component. It's a property of this normal vector field. And it is very interesting that the vice versa also. If you have such vector field which has this property, there always exists surface which will be orthogonal to your vector field. So it's necessary and sufficient. This condition is necessary and sufficient for the vector field to be the vector field of normal to some certain, orthogonal to some certain surface. If you have this one, you can define this surface. Of course, this surface can be, rigid motion is allowed. So surface you can shift some other places will be the same vector field. But only this. You can only shift surface, but not turn it and so on. It's a rigid motion. Not squeeze it or some other deformations. Only rigid motions are allowed. So this is